In the last concept video for this series, we shall discover the relationship between the power and brightness of a light bulb, as well as introduce a new unit that will help us quantify the household electrical consumption. We recall that power is the rate of doing work or the rate of transfer of energy. Power, therefore, is given by the equation P is equals to W over T, where P is the power, W is the work done or energy supply or energy dissipated, and T is the time. Hence, looking at this equation, the units of power is watts, or it could also be written as joules per second. Let us derive some equations that will be helpful to us when we calculate power. We know that power is equals to the rate of doing work, or P is equals to W over T. Let us substitute W is equals to QV into the equation P is equals to W over T. We will have P is equals to W over T is equals to QV over T. And we know Q over T is equals to current I, hence P is equals to I times V. This is my first important equation. Next, let us try substituting V is equals to IR into the equation P is equals to IV. So power is equals to I times V from our previous equation, and my V is also equals to IR. Hence, we have the equation P is equals to I square R. This is another very important equation. Lastly, let us make I the subject for V is equals to IR equation and substitute that into P is equals to IV equation. So P is equals to IV, where I is equals to V over R, and then we have P is equals to V squared over R. So here we have three very important equations. P is equals to IV, P is equals to I square R, and P is equals to V squared over R. The brightness of a bulb is dependent on the amount of energy generated by the bulb. Hence, the brightness of a bulb is directly dependent on the power dissipated by the bulb. The greater the power dissipated, the greater the brightness. Therefore, to see if a bulb is brighter or dimmer, we cannot just look at the current or the potential difference. We need to consider both factors and look at the power generated. Bulbs are typically given a rating, for example, 60 watts, 120 volts. This means that the bulb is meant to be used with an optimum potential difference of 120 volts, and when this optimum potential difference is used, the bulb will dissipate 60 watts of energy. If a lower potential difference is used for the bulb, the power dissipated will be lower and the bulb will appear to be dim. Now, if a higher potential difference is used for the bulb, the power dissipated will be high and the bulb will appear to be brighter. However, if the potential difference used is too high, a great current will flow through the bulb and cause the bulb to blow as the current is too high. When different potential differences is applied to the bulb, the current flowing through the bulb and the power dissipated by the bulb will be different. However, the resistance of the bulb will always be constant, as it depends on the material and the construction of the bulb. The resistance of the bulb can be found from its power rating. 60 watts, 120 volts, using this equation. P P is equals to V square over R. Hence, R, the resistance of the bulb, is equals to V square over P. Typically, in household or industrial usage of electricity, we do not use joules to measure the amount of energy used. Instead, we use a new unit known as kilowatt hour to measure the amount of energy used. 1 kilowatt hour is the measure of how much energy is used by a device that has a power rating of 1 kilowatt in the time of 1 hour. Hence, you can see that 1 kilowatt hour is actually the units for energy and not for power. Let us try and convert 1 kilowatt hour into joules. Okay, 1 kilowatt hour is the energy that is used by a device which has a power of 1 kilowatt. So 1 kilowatt is 1000 watts. Okay, within a time of 1 hour, which is 3600 seconds. This gives us a value of 3.6 times 10 to the power 6 joules.